We're doing it. We're talking about compilers finally. We have a new assignment out that is in a week. This one should be a breather compared to this last one. I know this last one was pretty intense, especially that last problem. But should be a bit of a breather before we get into kind of the very last end game content. So between now and the end of the class, we have about 2.5 weeks of actual class content followed by finals week. We have assignment this week. We have assignment next week. We have one last project that I'm going to get to as soon as I can. We have an exam next Friday and then a final. So still a good bit to go. Dwindling amount of time. Prioritize appropriately. And we started talking about compilers yesterday. Any questions on scheduling before we dive back into steps of compilation? All right, we gave an overall roadmap for what steps of the compiler look like. In fact, I should probably go back to that just so that we can refresh ourselves on the entire process. We talked about tokenizing via a scanner. We take as input our source program. The scanner is going to produce a stream of tokens at the end of that are read into the parser. And that is where we are as far as the steps that we have covered to date. So we talked about tokens and scanning. We talked about breaking down lines of code like this into their individual tokens. Have those tokens have types. And then passing those tuples on as that stream. We talked about implementing a scanner as a DFA, where you start in an initial state, and depending on the characters of the token, you can start to determine what the token type is and whether that token is defined or not. So pass in those characters as we reach a final state that says this is a token that we're aware of. Otherwise, you could have them that say things like this is a legal token in this language. So variables in Java, for instance, can start with certain characters and can't start with other characters. You could build that logic into a DFA where if you have a variable that starts with a number, that wouldn't be a legal transition from that initial state, and you would fail saying this is not a legal token. Then we get into the parsing step. Once we have a stream of token type pairs, we're going to, this is what we've talked about, this is what we've implemented with CYK. And this is the step we're going to come back to after we're done with all of this and talk about optimizing it. We use an existing grammar for the language, and we attempt to derive the program from the grammar. So starting from some start non-terminal, and we apply rules of that grammar in sequence such that there is a way to eventually produce the target source program. If we can derive it, it is syntactically correct, and we can pass it on saying it passes the syntax check. If not, then we return an error back to the user that says this program was not syntactically correct in the target language. As we do this, the parser is building the parse tree. What were the steps of the derivation in order to go from the start non-terminal to the target program as the depth first search leaves of that parse tree? Once we have that parse tree, we pass the parse tree on to the next step. So if the program is syntactically correct, the tree will be complete and represent the program. We then pass the parse tree onto the type checker. Let's give you an example. We're going to go through, instead of now looking at A's and B's and non-terminals and terminals in a very abstract sense, we're actually going to look at deriving a C-style program. So here are the rules of our language. Every program consists of a main method made up of a sequence of statements, each of which must either be an assignment, a print function, and that's it. So an example program might look like this. We're gonna take curly braces out of this, semicolons out of this, everything that we don't really need. But let's see if we can, with this idea of a language, go ahead and write a context-free grammar for it. And we're going to use BNF back as our form for this. So you would use non-terminals like program, sequence, line, variable, integer. You may need, I'm going to add one to this as well. You don't need to further define this one, but you may need to use it. Let's add. Let's add expression. So go ahead and relate these in the way that you have. Wow, that is a very slanted expression. In a way that we have prior in context-free grammars. So you're not trying to derive this program, you're trying to write the grammar for all of the rules that would tell you what a legal program is.
What's the difference between the sequence and the line?
A sequence would be multiple lines. The idea of a program is made up of either something that you can tell for sure, like this idea of main. We know that main starts the program. After that, we would have some sequence of instructions.
Let's hear for a minute.
Hmm?
Let's hear for a minute. This is amazing.
Wonder how that happened.
Wow.
Somehow everyone else completely ignored it and left it for you.
I don't know.
Oh, wow.
You're the subject matter. It's kind of help me.
Feel free to work in groups on this too. It does not have to be an individual task. So use expression on a right-hand side, but don't try to define expression, because that's going to be a lot harder than what we intend for the rest of this.
Can we just have like main A equals 4, or do we need A equals 4 and then we need to print A? Or like, do we need A and B every time?
No. So you would want a context-free grammar that recognizes any program that is going to be legal, not just this program, but a program that would be legal given the rules. That every program consists of a main method using exactly that syntax, made up of a sequence of statements, each of which is either an assignment or a print. How are we doing? Anyone think they're close? Who wants more time to work? Nobody. Apparently, we're good. So here is one possibility. Each one of these is a sequence of terminals and non-terminals. You can tell what the non-terminals are because they have angle brackets around them. So we're going to define a program as the terminal, the token main, terminal, the token open parenthesis, terminal, the token close parenthesis, followed by a sequence. So when we see a main method made up of a sequence of statements, we need to further define, we can now have a sequence of statements, which means that there are one or more lines defining what this program does. In this case, a sequence is made up of one or more lines, and the way we're going to do that is we can either have a single line or recursively define the first line followed by a sequence, one or more future lines. Then each of those lines is either an assignment or a print, so we have two possible definitions for a line. A line is either variable equals integer, and line equals the terminal print, the terminal open parenthesis, and expression, the terminal close parenthesis. And I didn't go in more detail and define what a variable is, but we could just assume that the only legal variables are A and B, or A and B and C, or every lowercase letter, or however you wanted to define what a variable is. An integer, you could define similarly to how we did on the problem on homework 1. But I think this is the important 4 lines of breaking this down into kind of the logic of the flow of a program. Any questions? So it's not totally complete yet, but at least it is started. Let's think about the parse tree. So I'm going to go back to the program here, and given these statements and given this program, what would the parse tree look like? How could we derive this program, main A equals 4, B equals 8, print A plus B, from this grammar? We have our start non-terminal, that's program. look something like this. And if we further drew this out, we would get something that looks like this. So we start with the start non-terminal program. From there, we would say, I don't really love this because there should be a couple more here where we have the open parenthesis, close parenthesis. So main sequence. Sequence is further broken down now into a line and a sequence. This line becomes an assigned statement. This sequence becomes a line followed by a sequence. This line is an assignment. This sequence is a line, which is a print. And when we have an assignment, we know the assignment takes variable equals integer. And we're really only looking at the non-terminals here. We're not making the terminals in this parse tree, but the way that I like to draw them out really involves all of those terminals and non-terminals. So we would have something like something that looks more like this. And this line was an assignment. So we would have variable equals integer. But that line, I think, was straight an assignment. No, it was strictly defined as that. We had and we have another. Basically, this process would continue until a depth first search through this tree would be reproducing the program as written on the prior slide. So we would have main, and this variable would become a equals 4, b equals 8, print a plus b. And from there, we would have a derivation from the grammar. This would tell us exactly how to derive the program from the grammar. The fact that we were able to do it tells us that it's syntactically correct. And this parse tree would be ready to go do some semantic checking, as we could start here. And when we see something like a variable equals integer, we would be able to just start doing some type checking. If the only variable type here is integer, then we could make sure that what this evaluates to is what this is expecting. And we would be doing a top down to figure out what are we expecting here? What is the type of the variable that we're declaring? What does this evaluate to? Especially if this was some kind of expression. What does that expression evaluate to? And that would be a bottom up. We would figure out what this evaluates to and then make sure at this line that what we're expecting and what it evaluates to match according to the semantic rules of language. So we know this already. As I've taught this more and more, I've gotten better at introducing things before the slides are necessary for it. How do we traverse the parse tree to determine the program output? That's just be a depth first search. We can also call that preorder traversal, whichever you prefer. So we get into type checking. Once we pass the derived parse tree onto the type checker, we're looking for semantic errors. Already mentioned a little bit of what that looks like. Some semantic errors are terminating, forcing the compilation to halt. This is just something that we can't evaluate as we're looking through it. But some of them would be non-terminating. So one semantic error would be a method takes two parameters, an int and a float in that order. The method is passed an int and a string. That is a semantic issue that this would catch. However, some semantic errors are allowed or have some built-in function that evaluates what is meant by that and goes through a conversion process. So same thing, method takes two parameters, an int and a float, and it's passed an int and an int. In Java, is this allowed? It is. Can you say double D equals 6? You can. You don't have to write 6.0 or something that evaluates to a float. You can write something that evaluates to an int, and it goes through a natural conversion into a double. Because there is a one-way, non-ambiguous path from an integer to a float. So what do? We just convert the int into its equivalent float. That's not something that you think about as the programmer. You just think, oh, that's allowed, I can do that. But it's on the compiler to be able to take in an integer and convert it into an associated float representation. What is the difference in the underlying representations of an integer and a float? Who recalls back to, what is that, 260? 160? Where do we learn the underlying representation of data types? 260? How is an int represented underneath the hood? You have 4-byte 2's complement. And at least in a 32-bit operating system and a 64-bit operating system, it might be 8 bytes, but it doesn't really matter one way or the other. It's the same idea. Some kind of 2's complement representation of an integer. How is a float represented? Float or double doesn't really matter. It's kind of the same thing.
Remember, there's an our IEEE standard for representing floats.
Yep, here's the IEEE standard made up of what components? There's the actual digits, and then there is an exponent field that moves where the decimal is within those. Those broken down into those components. There's actually a sign in front as well. So we have a sign, a magnitude, or the digits, and then a magnitude at the end. So that's not equivalent. You can't just shove a representation that is an integer into a representation that is a float. There's no easy conversion for that. That's something that has to be defined. When you take in an integer, what does that mean in terms of the actual digits and a times 10 to the power of representation of where we move that decimal? So that's actually the compiler that's doing that underneath the hood. But the programmer doesn't have to be aware that the compiler is doing it underneath the hood. It's like saying, what happens when you press the gas pedal? Car go forward. You don't need to know why, you just need to know the association. So from a programmer's perspective, you don't have to understand how it works. From a compiler's perspective, if you're writing a compiler or designing a compiler, you need to know that that's not something that you get for free. In fact, you don't get much of anything for free at the low level. You have to define when you receive something and the output is something else, you need to write that converter. So these are all things that type checkers will do. Do note, though, that there is no float to int conversion. So if we did this the exact other way, where we passed an int and a float, and we passed in a float and a float, there is no float to int conversion in some languages. In other languages, there are. It just goes through the floor. You pass in 7.7, and it gives you back 7. Stripping off everything after the decimal. But Java, for instance, does not. That is a semantic error. But there's nothing that says that you couldn't support that in your own programming language that you wrote. Or if you wrote a compiler for Java, you could allow for that, as long as you implemented it at the type checking step. Once we're done with type checking, we pass the parse tree on to intermediate code generation. And The goal of this is to produce simpler code. We want to convert a long sequence or a sequence of instructions that may be particularly long into a sequence of instructions that map to at most 3 memory addresses. Why is that? Those of you who can remember back to 260 or whenever you last learned assembly languages, why are 3 memory addresses important here?
Can you repeat the question?
Yeah, so we're changing lines of code to be sequences of lines of code that refer to at most 3 memory addresses. Why 3 memory addresses? What about assembly language cares about that number 3?
So if it's a function call, we would care about the location of the function, the current location to push onto the stack, and the location of variables.
Yeah, so if you do something like a move or an add or the basic assembly instructions, we need to know where is A, where is B, where is the result? The 3 memory locations for part 1, part 2, result. Every instruction is either representing 2 memory addresses like a move, source, destination, or something like an add. Left-hand side, right-hand side, destination. No assembly instruction refers to more than 3 memory addresses. So if you write something like A plus B plus C plus D, or even E equals A plus B plus C plus D in a Java program, what are the associated assembly instructions for that? We can't make that in a single assembly instruction. We need to break that down into a temporary A plus B, store the result, that plus C, store the result, that plus D, store the result, move it to E, move on. And each of those would be different registers where that's being manipulated from. It's not just where the variable is. We're not talking about registers, but let's give you an example. Turns something like this into something like this. So the intermediate code generation is trying to take complex statements and turn them into statements that map onto assembly instructions. Questions about intermediate code generation or why we do that? All right, once we have the same sequence of instructions that we had before, but now in a form, there are more of them, but they map to at most 3 memory addresses, we pass them on to the code optimizer. The code optimizer doesn't have to look at complex statements anymore. The code optimizer can be written for code that maps to at most 3 memory addresses, which makes the code optimizer a lot easier to write. This is where we're going to make an efficiency pass over the code, trying to make sure that we minimize the number of repeated processes that we don't need. So optimizations in the intermediate code. The question I would have for you is, let's look back at this code. Can the code that was generated be improved in efficiency? What can be done?
Remove 2 and in sum 2, just have sum 2 equal to 1 plus b.
Yeah, there's no reason to recalculate A plus B twice. Recalculate it after we calculated it and store it in a different location. If we could somehow cache that A plus B, especially knowing that we're going to be seeing that again in some capacity, we could just turn the prior slide into this. 1 fewer instruction, 1 fewer storage location. That's just overall better. But it also allows the programmer in the higher level language a lot more power to write programs the way that they want to write them. if you imagine that you had to write programs in Java as with full knowledge of a code optimizer and what the code optimizer was going to do so that you could remove the code optimizer step from the compilation process, the process of writing a program would be a lot harder. There'd be a lot more restrictions on what you can and can't do at the high level language. So rather than put the burden on the programmer, we write code optimizers in compilers so that developers can write code however they want. And it all becomes the same code at the code optimizer step. We can figure out how to make differences in programs equivalent and efficient at the compilation step. Once we've done the code optimization process, we have optimized code that refers to at most, 3 memory addresses. Then we just need to translate those directly into assembly instructions or machine code, whatever the target language is of this compiler. So temp1 equals A plus B. We're going to move A into register 1, move B into register 2. We're going to add register 1 and register 2 and move what's in register 2 back to temp1. So we now have a direct, easy translation from whatever the code might look like, just a map between that and assembly instructions. Any questions on this high-level process? Haven't really talked about the detail of exactly how this works, but kind of hopefully you see a picture now, kind of a flow of how we go from a high-level language down into a low-level language and what steps are necessary to ensure that what we have in the end result is efficient and now can be run or executed on a target architecture. One thing we haven't talked about is what data structures we need in order to make all of this happen. So we have a symbol table. The symbol table will tell us everything we need. It'll store the information about all of the identifiers. So in the current program, what are all of the variable names that have been created? What are the function names? And this allows us to do lookups. When we see a token that does not match to a keyword, we can do a lookup in the symbol table and say, has this been declared before? So as we scan, in addition to coming up with the token and the type, we're going to be writing to the symbol table. As we parse, we're going to get more information. At the tokenizing level, we don't really know what the variable types of things are. Especially if you're in you can just say something like, in Python, E equals 6. It's an expression and it doesn't have a type associated with it. In the interpretation part of Python, since Python isn't usually compiled, then during the parsing step, we will evaluate and figure out what the type of that is. So we can add that to the symbol table as we determine it from either the parsing or the type checking. Type checking refers to the table. When we are using a variable, we will look up that variable's type to make sure that expressions match to the expected types. So that's your symbol table. It really is just a table. Not more complicated than that. But compilers also go through error checking. Different kinds of errors that we can see as we go through this process. As we scan, a token that we find might not match a particular token type. So we see some word and that word doesn't match something that we are familiar with. Either it hasn't been declared, it doesn't match to a keyword, it's just gibberish. So we can return an error at that point. In the parsing phase, we may not have a production, a right-hand side that matches to an expected grammar production. So that's a syntax error. In the type checking, We have semantic types of errors, type errors. When we find an error, we need to make sure that we record important information about it so that we can return it to the user so that the user knows what happened. When you execute programs and you get errors, especially errors that aren't from your own error checking, it's the compiler that's throwing that. It's returning something useful back to you so that you can know what happened so that you can go fix it. If you're writing a compiler, then you need to make sure that all of the error checking that is the compiler's responsibility is something that is done in a communicative way, a way that returns the most useful information back to the user so that the user can go fix it. That's basically it. That's a very high level view of the steps of a compiler. And if there were a part 2 to this class, I would have people implement a compiler for a simple language. I would have a simple C-like language like the last example, and I would say, let's go through and write every step of the compiler so that we could write programs in this basic language and have them work. Unfortunately, we don't have time for that, so I have to pick and choose what we do from here with the last couple of weeks we have of our class. So we're going to hone back in on parsing. This is the broad overview of compilers. But to me, the hardest part of a compiler is the parsing. Especially to get in an efficient manner. You don't want to, when you finish writing a program and you compile that program, you don't want that process to take a long time. You want that process to be fast. So let's talk about parsing. We've talked about parsing a good bit, but let's see if we can recap it. Anyone want to recap as far as the parsing that we've seen this quarter? What have we tried? What was the efficiency?
CYK.
We tried CYK. We also talked about something before that that wasn't so good. Brute force parsing. Yep. So brute force parsing had exponential complexity. That's disgusting and gross. CYK had cubic complexity. So we talked about, brute force, exhaustive search. We had issues with that because if there were multiple possible productions for a particular left-hand side, we had to explore both of them. And that creates an exponential tree, exponential branching factor, and complexity was gross. CYK, cubic. We're going to get into LL parsing. So we only looked at it briefly. We're going to look at it in a lot more detail. But before we zoom in on LL parsing, we should talk about the different ways that we can parse. So there are two main parsing approaches. The first is a top-down approach, where we start with the start non-terminal and over time replace left-hand sides of the grammar with right-hand sides, with the goal of eventually deriving the query program. Start with the start non-terminal, iteratively replace things, end up with the program. So brute force was a top-down approach, and LL parsing is also a top-down approach. In a bottom-up approach, we start with the actual symbols in the string. What is it that we are trying to derive? Either the program, the string, and we are going to move through and replace portions of the string with non-terminals. So we're going to go from right-hand side to left-hand side in the grammar, replacing right-hand sides with left-hand sides, until we eventually derive the start non-terminal. So CYK is a bottom-up approach. And it turns out that LR, the very last thing we're going to talk about in this class, is also a bottom-up approach. So we'll have seen two different top-down approaches and two different bottom-up approaches. Although brute force really shouldn't be called an approach because no one should ever use it. I'll give you some examples of what this looks like in practice. Here's a grammar. Go ahead and construct a leftmost derivation and parse tree for it doesn't actually have a string. I don't think it actually matters. Do this for some string. Construct some kind of leftmost derivation and parse tree. We could end up with something like this. And then like this. And eventually we get some result. So S arrow, we see that that produces the A capital B, C. From there, we expand the A and the B, and we end up with a string AA, BB, CBC via a depth first search of that tree. So the process that we went through is we started with the start non-terminal. We replaced the S with a right-hand side. We replaced the A with a right-hand side. We replaced that A with a right-hand side. We replaced the B with a right-hand side. We replaced that revealed B with a right-hand side. And at that point, there were no further non-terminals, and the leaves in depth first search order gave us the string. So that is a top-down parse. A bottom-up parse, on the other hand, you can do something like slowly replace terminals with non-terminals. So we could start with AAB. You use the production capital A arrow B and replace the B, the right-hand side, with its associated left-hand side. Then we see A capital A, and we can replace that with a capital A. We replace the C with a capital B. And we continue to do this until we derive the start non-terminal. This is kind of a fancy way of seeing what CYK did. We were making those non-terminals when we filled in the middle portions of CYK with the associated non-terminals. That was middle parts of this bottom-up process. And we knew we were successful when we derived the start non-terminal in that top left box. That said that it was possible to start with the start non-terminal and produce the string. But we didn't start with the start non-terminal, we started with the string at the very bottom. So that was very much a bottom-up approach. How are we doing? Any questions before we dive into the concepts that are going to reveal the LL parsing process? It's going to involve advanced analysis of grammars. So we're going to dive into looking at grammars like we haven't before. All right, the first thing we're going to look at is unironically called the first function. The first function's goal is to tell us which of the possible applicable rules we should use in a top-down or bottom-up parse. So there are going to be two functions that we're going to look at to be able to do this. There's first and there's follow. We'll start by talking about first. So the first function says we take as input a context-free grammar, and the output of first are the set of terminals that could be the first terminal of a derived string starting at that non-terminal. So that's going to involve a sequence of rules. So first can be defined for any string or substring. The first of just a terminal is the set that includes itself, and that is it. So first of lowercase a is the set that contains lowercase a. First of a non-terminal is going to be an iterative process. It starts as the empty set, and we're going to go through an iterative process of exploring the grammar. As we explore the grammar, we're going to be adding values to this first of a non-terminal. As you do this, you're going to be adding strings to this first, and those strings are going to need to be further evaluated as the first of that, kind of as a recursive process. So the first of a left-hand side is defined to be the union of the first of each production in the right-hand side. So if we have S arrow something or something else, first of S is going to be first of the first right-hand side and first of the second right-hand side, the union of those two. The first of a production is defined to be the first of the first symbol in the right-hand side of that production. But there is a reason why this isn't just why we have to write the entirety of the production here. So here is the associated pseudocode for how to construct first. And I will be revealing this slide deck because you will be referring to this in your second project. In fact, don't forget about that. There are significant hints for how to construct this on the slides when you go to, you're going to be implementing LL parsing. And to do an LL parsing, you need to define a first function. Let's give you a quick example. Here's a grammar, and we want to determine the first of S for this grammar. This tells us that the intuitive way to read this is in any possible derivation where we could start with the start non-terminal, what is the set of terminals that could begin strings? So is there at least one string in this grammar, starting with the start non-terminal, that could begin with the terminal A? Is there a string that could start with the terminal B? Is there a string that could start with the terminal C? We will be adding to the first as we go through and prove that at least one string starts with that terminal. So following the rules on the prior slide, we can say that first of S is defined to be, we'll start out with itself to be able to get the empty set. Union the first of every right-hand side. So there are two possible right-hand sides, S arrow A capital SB or capital A. So we're going to add both of those as the first to the right-hand side of the first of S. So first of S is defined to be the empty set so far. We're going to union that with first of lowercase a capital S lowercase b. The first of that is going to be the first of the first character in it, which is just a lowercase a, and the first of the terminal is defined to be the set that contains itself. So that's how we get the first of lowercase a as the second component. And then we have a first of another non-terminal, which we will have to recursively now go calculate and define. So first of A is going to start out empty, but it will be unioned with the first of the right-hand sides of the A productions. So that will give us first of A, empty set, first of B capital A, which is just the first of lowercase b, which is the set containing lowercase b. Then first of lowercase c is just the set that contains itself. So first of A can now be recalculated as B and C. So now we can go back recursively. We're going to end this recursive call, go back to first of S, replacing first of A with the set that we've calculated B and C. So we get A, B, and C. And this is a proof of every first character of a string in this grammar. Questions on that? Any questions at all about how that was derived? All right, we will come back tomorrow and explore this in more detail, including the edge cases that make this a little bit more challenging. I think I mentioned yesterday, but I don't have my typical 10 to 11 office hours today, but I will be in my office from about 12 to 3. So feel free to stop by if you have any questions that I can answer at that time.